have seen this image everywhere. Seriously, it's the symbol for science, for atomic energy, for genius. You know the one. The planetary model of the atom, with little electrons zipping around a nucleus like planets orbiting the sun. It's simple, it's elegant, and it's completely wrong. Today, we're going to dive into the story of this iconic but flawed model and the brilliant mind who dreamed it up, Niels Bohr.
Okay, so let's get right into it. Why is that picture, the one we all know, not actually what an atom looks like? Well, the answer is tied up in this huge crisis that totally rocked the world of physics at the start of the 20th century. A crisis that was so deep, it demanded a solution so radical, it would literally change how we understand reality itself.
All right, let's set the scene. It's the early 1900s, and scientists are just starting to peel back the layers of the atom. I mean, they knew it existed, but they had basically no idea what it looked like on the inside. So this was a time of just intense discovery and even more intense confusion.
And the pace of discovery, it was absolutely breathtaking. Think about it. In less than 10 years, our picture of the atom went from J.J. Thomson's kind of vague plum pudding idea in 1904 to Ernest Rutherford's revolutionary nuclear model in 1911. And that discovery is what set the stage for Niels Bohr's game-changing leap just 2 years later in 1913.
So this was a huge shift in how people thought about things. Thomson imagined the atom as this sphere of positive goo with electrons just kind of stuck in it, like plums in a pudding. But Rutherford's famous gold foil experiment showed that was just impossible. He proved the positive charge was packed into a tiny, dense nucleus, with electrons orbiting way out in the distance. It was a massive step forward, but funny enough, it created an even bigger problem.
And here it is. Here's the crisis. Rutherford's model, as revolutionary as it was basically doomed from the start, at least according to the laws of physics they knew at the time. It described an atom that couldn't possibly exist for more than like a fraction of a second.
Okay, so here's the really big problem. Classical physics, the physics of Newton, predicted a total catastrophe. See, an orbiting electron is an accelerating charge, and any accelerating charge has to radiate energy. As it loses that energy, its orbit should decay, sending it on a death spiral right into the nucleus. An instantaneous collapse. But that's obviously not happening, right? We're here. The universe exists. Atoms are stable. Something was fundamentally broken with physics itself.
And then enter Niels Bohr, a young, brilliant Danish physicist working in Rutherford's own lab. He saw this death spiral problem not as a failure, but as a giant clue that the old rules of physics, they just didn't apply inside the atom. He was about to propose something truly radical.
The key to his whole idea was this strange new concept from Max Planck called quantization. All it really means is that certain things, like energy, can only exist in specific, discrete amounts, not in a smooth, continuous range. The best analogy? It's like a ladder. You can stand on the first rung or the second rung, but you can't just hover in between the rungs. Bohr basically said, hey, what if an electron's energy inside an atom works just like that ladder?
So Bohr just threw out the classical rulebook and wrote his own. First, he just declared that electrons exist in these special stable orbits where, like magic, they don't radiate energy. Death spiral, problem solved. Second, he said they can jump between these orbits, but only if they absorb or spit out a perfectly sized packet of energy, a little particle of light called a photon. And third, he came up with a new quantum rule that specified exactly which orbits were allowed. It was bold, it was definitely weird, and it was about to solve a huge mystery.
You see, for decades, scientists have been totally stumped by the light that hydrogen gas gives off. When you heat it up, it doesn't just glow with a nice, continuous rainbow of color. Nope, it emits light only at these very specific, sharp lines of color. It was like a barcode for hydrogen, and nobody could explain why.
And this is where he had his aha moment. A friend showed Bohr this old kind of obscure formula that a Swiss schoolteacher named Johann Balmer had figured out years ago. It didn't explain why the lines were there, but it perfectly described the mathematical pattern. For Bohr, looking at that formula with his new rules for the atom in his head, everything just clicked.
So, here's how his model just worked its magic. Imagine an electron is in a higher energy orbit, one of the top rungs of the ladder. Eventually, it's going to fall back to a lower, more stable one.
And when it makes that jump, the extra energy it had has to go somewhere. It gets released as a single particle of light, a photon. And the color of that light corresponds exactly to the size of the jump. A big drop down the ladder, you get a high-energy blue photon. A little tiny hop down, You get a lower energy, red one.
And this was the model's crowning achievement. All of a sudden, that bizarre barcode of hydrogen made perfect sense. Each and every line was just the signature of an electron jumping between two of Bohr's special allowed energy levels. His strange rules weren't just some crazy theory. They predicted reality with stunning precision. It was a monumental, world-changing triumph.
But you know how science works, right? The story is always about progress, not perfection. Bohr's model was an absolute masterpiece. It was the crucial bridge between the old classical world and the strange new quantum one. But it was just that, a bridge, not the final destination.
Yeah, as brilliant as it was for hydrogen, the model just kind of fell apart when you tried to apply it to anything more complex. It couldn't handle helium with its 2 electrons. It had no explanation for why some of those spectral lines were brighter than others, or why, if you looked really close, they sometimes split into even finer lines. And by the 1920s, a much more complete and, honestly, much stranger theory, quantum mechanics, came along and showed us that electrons weren't tiny little planets at all, but more like fuzzy clouds of probability.
And yet, the Bohr model lives on. Scientifically, it's obsolete, but culturally, it's immortal. From the flag of the International Atomic Energy Agency to the logo for the Big Bang Theory, this simple, intuitive picture of an atomic solar system has become the universal symbol for science itself. And why? Well, precisely because it's so easy to grasp, even if it is wrong. So, the story of the Bohr model leaves us with this really fascinating question, doesn't it? It was a brilliant, necessary, and, in the end, an incomplete step on the path to truth. It really makes you wonder, which of the rock-solid scientific truths that we hold today are just the beautiful, flawed models of our own time, just waiting for the next Niels Bohr to come along and take that next quantum leap?